So these guys live Connect IQ in and out every day. Brendan and Coleman, raise your hand. They're the ones you've been, if you haven't met them already, they're the ones you've probably been interacting with on the forums, and probably should save this for because they're next, but when you don't give Coleman grief, because you can see he's very tall, and okay, so I wanted to intro this. I'm going to let Marianne and Brian speak, because they are, Marianne has taken over the compiler for me, so if you've noticed, it works better in the past 6 to 8 months. Marianne is the reason. We are so lucky to have her on the team. Brian is one of the original 3. Brian actually has been with Garmin for how many years now?
Almost 10.
Almost 10. He worked on Forerunners and Edges for many, many years, and I was lucky that he came over to the Connect IQ team, and he works on the virtual machines. And I'm here to answer questions like, why did you do it this way? Because, so in the history of Connect IQ, there was an initial year where it's my code, and then they inherited it, and I said, have fun with that, good luck, and more specified roadmap, and you're better off for it. So the goal of Monkey See from the get-go was to try and make, easy was job one. We wanted something that was, you could look at, it was like the Spanglish of languages. There's a little Ruby here, there's a little Python here, it had to be high level, the dynamically typed, it was in vogue, there's dynamically typed versus statically typed, and dynamically typed, it has its, on the web, is much more popular on the web side, statically typed, it's, more server side, and I will openly admit, part of it was that first compiler didn't, now that I know a little more, statically typed probably would have been the way to go, but I was more a VM person, so sure, that's where we went. It has a very high, the goal was to make something very high level with JavaScript syntax, but at the same time, take out the features that would have been low performing on embedded hardware. So that's why it's very goopy, but you don't have first class functions, because we didn't need every function taking up a memory handle. And also we wanted to hide from you what the Garmin developers have to deal with every day. We were trying to make it very, the Garmin developers are, straight embedded C, our environment, and we didn't want you to have to feel that. We wanted to make it feel like it was a very easy to use environment. And so the goals were easy, but performance, portable, so that we could try and enable you to work across multiple devices, and future-proofing. To some degree, we wanted to start somewhere that as we grew, as new processors became available, you didn't have to worry about, this one has our 4-byte alignment access, and suddenly your app doesn't, what you compiled on this doesn't work on that. So using a high-level bytecode engine seemed to make sense. So to get you thinking about where we live, I'm going to talk about in principle and in practice. In principle, we are providing a high-level programming language for embedded systems. But in practice, we anger everybody. The high-level people are like, where's my first-class functions? Where's my, why does the typing take up memory? And the embedded people are like, I want a byte array. Where's my byte array? It's like we wanted it simple, so arrays are very flexible, and we tried to but in some ways we made some language decisions to steer you away from doing certain things. Like there's no linked list, because as we'll be talking about, since we have no MMU, we're using memory handles, and we had a fixed number, and encouraging you to use dynamically sized things would actually have you run out of objects faster. In principle, we provide tools like objects, inheritance, dictionary, strings, things that you're familiar with, things that you've been using for years. In practice, please don't use any of that. Have you heard of an int? Like, number, it has 32 bits. You can represent 32 things with them. No, I mean, it's not like we necessarily want to hide that. It's just that you have to, like, and Brian and Marianne will be getting to some of the performance choices you should make or you should think about. Because one of the challenges with dynamically typed languages, it's harder for the compiler to make decisions for you. It's harder for it to make optimization choices for you because it's so dynamic. And the Monkey C compiler actually knows very little about your code from the get-go. It's like, sure, I'll put that on the VM and let's sort it out. But that means that there are some optimizations you can do in coding that maybe someday the compiler will get smarter. But if you think in it, if you know or can think in embedded space, that's probably for the best. In principle, we have an easy-to-use HTTP API. And in practice, don't download it, I think. So don't fear. It's just that we have in our BLE connection between the wearable and the phone is at around 2 kilobytes per second. And we have limited memory. So if you hit something like the Twitter API, and it has like every known thing about the person in the tweet, you will blow our heap space before you ever get your information. So that's why sometimes we either encourage creating endpoints or proxy endpoints that are more wearable focused that will reduce the communication lag time between your request and your response. So we provide a high-level drawing toolkit with bitmaps and drawing functions to let you customize your user experience. And we'll fix DrawArc. It's going to work someday. Brian has a Jira. He's going to make it happen. Like, one thing, like, so Garmin has its own custom OS, custom drawing toolkit, and ConnectIQ exposed, like, we put wrappers around it, and then we discovered that by exposing it to developers, you were finding bugs that have been in Garmin code for years, and the Garmin solution was always, well, we'll just not do that. And that's harder for us to tell you. So this is like, but it does take time for, in the next talk, I think Brandon Coleman will be talking about why, how to report those kinds of issues, and why it can sometimes seem to take forever for those to propagate. So at this point, I am going to hand over to Marianne, who's going to start talking about the language. And oh, I should also encourage you to ask questions along the way if you have any questions about the content. But Marianne.
Okay, so we're going to just start out by just reminding everybody about a few Monkey C fundamentals. So first, all objects within Monkey C inherit from the base toybox.lang.object class. Also, Monkey C is duck typed. Duck typing just means that the compiler does not actually verify type safety. In fact, variable types are never declared. Instead, if you somehow mishandle an object, the VM is going to tell you about it. So this really gives our developers the added advantage of being able to store mixed types within the same container, like an array or a dictionary. So in the first example on this slide, you'll see that we declare an array where we're storing an integer, a float, a double, and a string. At the same time, Monkey C is reference counted, which just means that all references to an allocation is actually tracked by our runtime system, which will then immediately free memory when all references to an allocation is no longer remain. So we'll note an important vulnerability to reference counting is circular references, which is just a cycle within your reference chain. So in the second example on this slide, you'll see we have a function where two arrays actually reference each other. Once we return from that function, those references would just stick around and leak memory until your application terminates. So circular references explicitly avoided at all costs. We also realize that sometimes objects really do need to reference each other. In this scenario, we allow for a weak reference, which is just a reference to an allocation that doesn't actually increment our reference counter. So once all strongly bound references are freed, So getting the weak reference will just return null. However, for all you Portal fans out there, we also have the still alive method call on a weak reference that will tell you whether or not a reference is still alive, courtesy of Nick Crawl, of course.
It was in prime.
All right, next I'm going to talk to you a little bit about memory management. So these days, you all probably would consider memory management a relic of the past. Memory is plentiful, it's cheap, we can jam it into everything in huge quantities. I found out recently when shopping for refrigerators that you can buy one with Android on it. It's crazy. However, we're trying to put something on your wrist that has more than a day of battery life, and that still requires specialized hardware, which means we have low amounts of system memory and we have no MMU, as Nick mentioned earlier. As a result of this, we currently have a static limit on the number of objects that can be created by any application at one time. This limit exists because the way the heap tracks that memory requires some memory from the application. Before your process even starts up, we have to take some of your memory to do that tracking. We don't want you to have to continuously worry about how many objects you have, but we also don't want to take all of your memory before you even get started. So we've attempted to balance these two issues as best as possible. Continue to evaluate that as our system requirements change. Most basic monkey see objects do not require an allocation, so they come essentially free to you. These are objects that you would expect to fit into 32 bits. That includes the ones up here: nulls, numbers, floats, strings, symbols, booleans, and characters. Our other built-in types do require an allocation, but they are generally much smaller than a custom class definition. Those include strings, arrays, dictionaries, longs, doubles, and weak references. We apologize for the presence of long and double on this list. We haven't figured out how to get 64 bits into 32 yet, but we're working on this. There's a few common ways that you might run into trouble with allocations in Monkey C. The first of which is large JSON responses from web APIs. These are frequently constructed out of a large number of small strings in the JSON payload. This may not take a ton of your application memory, but they do use a large number of allocations. When possible, you'll want to limit the data that you're downloading from the web to the things that you actually want to use in your application. Some public APIs like Twitter, as Nick mentioned, may be difficult to use unless you have a middleman service that can repackage that data. The next thing that you'll want to be careful with is large sets of longs and doubles. One thing to really keep in mind here is that any math operation you do with a long or a double is going to return a long or a double as a result. So if you don't need that extra precision after doing calculations, you'll want to manually recast those back to floats or ints. The last thing to touch on here is two-dimensional arrays. We've got an example. Monkey C does not natively support two-dimensional arrays, so some of you may have created one dynamically, as you can see in this code here. But in the example, we can see that the first version creates a 2x100 array, and it ends up with 101 array allocations. But simply flipping our indice order can give us the same functional array with only 3 allocations. The next thing I'm going to talk about is the speed of variables at different scope levels. Variable lookups are done on the VM because of the duck typing, and they're going to start at the narrowest scope and seek outward. This means that every level of class inheritance that you have to look through is going to slow things down a little bit. Stack variables are accessed directly by the VM, so it's best to use them as much as possible. In this example, we see some code that's going to sum a list of values from an array into an instance variable. In the first version, it's adding it directly into the instance variable for every iteration of the loop. In the second version of the example, it instead sums them into a stack variable and then adds them to the instance variable after the loop. So the second version is going to be a little bit faster in executing on the VM because that instance variable lookup would have to happen every single time through the loop on the first one. The last thing to note is that global variables are at the widest scope. And so they're going to be the absolute last thing that the VM looks for your variable in. We've provided the $ operator to access the globals directly. This allows you to tell the VM this is a global variable, and it'll just go look there straight away. The same can be done with module level variables. So you can specify the module that you're looking in, and it'll go straight to that module instead of seeking up through your class chains first. Another thing that can slow your application down is repetitive object creation. And one kind of hidden culprit might be that you might run into are string constants. String constants, when they're found in your code, are going to get loaded out of the data section and turned into an object every time they're encountered. So in this example, I've got a function that I made up that takes an array of times and turns them into an array of string formatted times. And in the first version, it's got a couple of string constants that it grabs inside the loop, as well as doing string addition multiple times within that loop. The immutable aspect of monkey see objects means that a new object is going to get created and stored into that variable every step, every time that addition happens. So that's going to be a ton of object creations that are happening in the loop. The second version of the function instead uses the lang.format method in order to do that string formatting in one step. We've also taken our string constant and stored it into a stack variable before entering the loop so that that string constant doesn't have to be loaded from the data section and create an object with it each time through the loop. Another simple way that you might want to reduce the number of object allocations happening is to use as many of those basic types we talked about before whenever possible, the types that can fit into a 32-bit space. Now, Marianne is going to cover some topics that relate to the monkey see compiler.
Okay, so so there are a few different types of resource objects that you can use within monkey see. These include bitmaps, fonts, and strings, which can all be loaded as needed by your application. So it's important to keep in mind that these loads are from disk, so they're expensive, they're not quick. You should always load your resources when the context actually changes to one where the resource is required. So typically for views, this is going to be in your onLayout call. And because it's on disk, it's the load from disk, it would not be great to load resources as they're being used or on demand. So in an on-update call, which really should only be used to update dynamic content, you would not want to load resources. Additionally, bitmaps can take up a significant amount of memory when loaded. One good way to reduce the impact on your memory is to use reduced palettes. If your image doesn't actually require full color depth. So the example on this slide just shows a bitmap icon with a color palette that is just limited to black and white. And I'll also note transparency of an image is always going to be implicitly included unless you disable it explicitly within your bitmap definition. So one really cool feature of the monkey see resource compiler, in my opinion, is build exclusions. These are just a great way of removing excess code from your project. Build exclusions basically allow you to just build different sets of code based off of your product configuration. So, for example, implementations may vary drastically between handhelds and wearables. So on this slide, we just show a couple of different ways to use these exclusions in this scenario. So as you can see, within your resources file, you can exclude specific code depending on an annotation. So you might have shared code between the two, and you could just annotate what you want excluded. You can also exclude based off of entire source files or even directories. So the default resource file in this example would exclude the handheld directory, while the handheld resource file would exclude the wearable directory. So we've made it to the exciting stuff. New things introduced as part of the 2.3.0 SDK. So the monkey see resource compiler can now read static JSON data and store it within your app executable and be loaded at runtime. This is going to just be useful for storing large amounts of data and not having to keep it within active memory at all times. So the example on this slide just shows the two different ways that you can declare JSON data in your resources file. One way is just to inline it directly within the JSON data tag, or you can just throw all your JSON data into a file and reference that file within a JSON data tag. Then you can just load that JSON data during runtime using a watch UI load resource call. And then something near and dear to my heart, we humbly present to you switch statements. Our switch statements are going to be very similar to other control statements of this nature that you probably used in other languages. The implementation makes sure that we're backwards compatible with 1X devices, as well as supports case falters.
Yeah.
Okay. I expected more applause. And then it's also just going to be more powerful because of the way Monkey C is typed or lack thereof. You're going to not be limited to switching on a single type. So as you can see in this example, we switch based off of whether it's an instance of my class, if it's string, or if it's an integer. Yeah. We are all I live for it. We also are announcing the new keywords public, protected, and private. Class members by default are going to be public if not explicitly declared as such. Protected is going to be synonymous with existing hidden keyword behavior. And then private keywords will be only accessible to the class that they are defined within. You're welcome.
All right. The next feature we're going to talk about that's new in 2.3.0 is background services. So we've got the ability for applications to register for background service. These services are going to be loaded separately from the main application and have a separate permission set. So for example, they're not going to be able to access any of the user interface modules for obvious reasons, but they will have access to the communications module even when they're registered via WatchBase. Services are required to fit into a smaller memory footprint than your main application. So if your main application is too big to fit into that space that's allotted, you may find that your service is not able to be loaded. If this happens, you're going to need to use the new background annotation that we've added specifically for this case. This allows you to specify what code sections should be available to your service. In this example, we have the background annotation applied to a function within a class. You'll want to note that those annotations are going to be inherited up a class chain. So putting the background annotation on this method here is going to actually cause the entire class foo to be pulled into the background service section. If you're using the background annotation, so your whole application isn't being loaded to the background section, attempting to access any classes or methods that are not annotated are going to cause an application error and it'll exit. One other thing to note about the annotation is that it isn't inherited up to the module level, so you are able to use it to bring in some portions of a module but not others. And then the last thing to keep in mind is that anything you annotate as background is still available to your main application. It doesn't get excluded from that other main application process. So restrictions that we have on background processes is that they're going to have a maximum of 30 seconds to complete what they need to do. We think that most of the things that you guys are going to want to do are going to be much shorter than this, so you'll want to exit as quickly as possible once you've completed your actions. Some things you might want to be staying open for is waiting for a response from a web request or waiting to connect to a sensor and get some data. Things that you shouldn't be trying to use background processes for is crunching data, trying to do computation. If you do this too much, you might cause an impact on the user's battery life, and that may cause them to give you a bad app review. Services can send data, once they've completed, to the main application using the exit function in the background module. The data that is sent from that exit function is going to overwrite any previously saved data. So if you need to save a history of data points from previous background runs, we've added an API. We have an API in the background section that allows you to read the previously saved data. You can merge it with your new data and then save it out when you exit. The last feature to talk about for our presentation today is the always active watch faces. So with the addition of always active watch faces, ConnectIQ can now update the display every second. Now, Nick already mentioned this in the presentation this morning, but there is, of course, a catch, because there's always a catch, and that is that always active watch faces are going to have to execute within very strict time limits. The updates at the top of each minute are going to be exactly what you've expected from previous versions of ConnectIQ, and there's a new partial update method that is going to be added for all of the seconds in between. If your partial updates are not quick enough, the application is going to be notified via delegate callback about the power budget exceeding that it's caused, and the partial updates will stop until the next time the application is closed and reloaded. The first thing to keep in mind when trying to optimize your always active watch faces is that ConnectIQ code is executing on a virtual machine. Virtual machines aren't exactly the fastest way to run code. Sorry about that. Because we're emulating a processor of software. So the first thing to do is to try to minimize the amount of code you're executing. So if you can reduce the number of lines of code that you're running during the partial update, that's going to speed up your process. One thing that can really help out here is pre-computing as much of your layout information in your layout methods. Another thing to keep in mind is resources. Attempting to load resources in a partial update, they're coming from disk, and that will cause you to basically instantly exceed your budget. So those will need to be loaded in layouts or the main updates at the top of the minutes. So to go along with always active watch faces, we've added a number of graphics features to help you meet the requirements that we're imposing. The first tool we've added is the new buffered bitmap class. Buffered bitmaps allow you to keep a graphics buffer that's separate from the main screen. In our analog SDK sample, this you can find in the SDK and check it out, we are rendering analog watch hands over some background graphics. These background graphics are admittedly not very complicated, but I know you guys will come up with much more complex things, and attempting to render those during the partial update wouldn't be a very good idea. So in here we can see a little bit of code pulled from the analog sample where we're generating an off-screen buffer for the background image. Now a full-screen buffer with all of the colors available to the system is going to be really large, so we've limited the color palette to just the grayscale colors. This makes that bitmap much smaller. Then we render our background graphics into that and then copy them into the main buffer during the partial updates as a full image that's been pre-constructed. The next thing that you'll need to take into account is the time it takes the device to actually copy the pixels you've modified over to the display. The device has to physically transfer these modified areas to the display hardware, and updating the entire display takes way too long for partial updates. Now our graphics methods aren't able to specifically track the pixels that you're modifying, so we've instead added a clipping tool that allows you to let the system know what you're modifying. Clipping areas are going to be able to be applied to the main DC object or one that's generated from the buffered bitmap objects. When a clipping area is applied to one of those objects, any draw calls that are made to that object will only draw within the main portion. Any pixels that would have been modified that are outside that region will remain unchanged. If you attempt to update the display during a partial update without using one of these clipping areas, you're going to exceed the power budget pretty much instantly. The image here from our analog sample, you can see that we only need to update the area within that box where the second hand is. So in this code example that's pulled from there, you can see we're computing the coordinates for that hand, watch hand, to draw it. And then we determine what the bounding box is around that hand and set a clipping area before drawing that to the screen. The last issue that we need to address regarding always active watch faces is anti-alias text. So anti-aliasing fonts onto a buffer requires the native anti-aliasing screens in the devices, which means it's not able to be done on palleted surfaces. So we created this nice background image with a palleted surface to save our memory, but now we can't render this date font into there, and we've got to draw the watch hands over it too. So to resolve this issue, we just use a second buffered bitmap. Here's another sample from the code, and we generate an off-screen buffered bitmap for that date text, and it's sized just to the size of the text to keep the memory requirement low. And then we can render the date into it in the normal on update methods, and then we copy that into our main buffer before rendering the watch hands over the top of it. So that's all the topics we have. We'll let Nick give us a little wrap up, and then we have plenty of time to take questions and